Welcome to our exploration of DC generators and motors. At its core, a DC generator converts mechanical energy into direct current electrical energy. The magic behind this transformation lies in Faraday's law of electromagnetic induction. When a conductor moves within a magnetic field, an electromotive force, or EMF, is induced. This fundamental principle allows us to generate electricity through motion. The key takeaway is simple. Movement within a magnetic field creates electrical potential, powering countless technologies we use today. Let's dive into the basic working principle of DC generators. Faraday's law states that when a wire moves in a magnetic field, an electromotive force is induced. Accompanying this is Lenz's law, which explains that the induced current will always oppose the motion causing it. In a DC generator, a coil rotates within a magnetic field, cutting through magnetic flux. As this happens, the generated voltage is collected by commutator rings and brushes, ensuring a smooth and directional electrical output. Now, let's explore the key components of a DC generator. The armature is the rotating coil where EMF is induced. Field windings, which can be electromagnets or permanent magnets, create a stationary magnetic field. The commutator acts as a mechanical switch, reversing current flow to ensure unidirectional output. Brushes, typically made of carbon or graphite, maintain electrical contact with the rotating commutator. Finally, the shaft connects to an external power source, providing the mechanical input energy that drives the entire system. DC generators come in different configurations, each with unique characteristics. First, we have separately excited generators, where field windings are powered by an external source. Self-excited generators use the generator's own output to power field windings. Within self-excited generators, we find three subtypes: series wound, where field windings are in series with the armature; shunt wound, with windings in parallel; and compound wound, combining series and shunt windings for enhanced performance and versatility. Let's walk through the working mechanism of a DC generator. It begins with creating a stationary magnetic field using field windings or permanent magnets. The armature is mechanically driven, typically by a turbine or motor, causing it to cut through magnetic field lines. According to Faraday's law, this motion induces an electromotive force across the coil. The commutator plays a crucial role, reversing current direction to ensure constant, unidirectional output. Brushes then transfer this current to the external load, completing the electricity generation process. The induced EMF in a DC generator is described by a fascinating equation. E equals P multiplied by phi, and Z divided by 60 and multiplied by A. Breaking this down, E represents induced EMF, P is the number of poles, phi is magnetic flux per pole, and is armature speed in RPM. Z is the total number of armature conductors, and A represents the number of parallel paths in the armature. This equation helps engineers precisely calculate and predict the electrical output of a generator. DC generators have numerous practical applications across various industries. They are essential in battery charging systems, providing steady DC voltage. Small power plants utilize these generators for DC power generation. In welding, DC generators supply the critical current needed for arc welding processes. From maintaining power in remote locations to supporting industrial manufacturing, these generators play a crucial role in our technological infrastructure. Transitioning to DC motors, these remarkable machines convert electrical energy into mechanical energy. Operating on the Lorentz force law, a DC motor demonstrates how electrical current interacting with a magnetic field creates mechanical motion. When DC voltage is applied to the armature, current flows through its windings. This current-carrying conductor interacts with a magnetic field, generating a mechanical force that causes rotation, ultimately transforming electrical energy into useful mechanical work. The construction of a DC motor involves several key components. The armature is the rotating part where current interacts with the magnetic field to produce torque. Field windings, either stationary windings or permanent magnets, create the magnetic field. The commutator acts as a mechanical switch, reversing current direction to maintain continuous rotation. Brushes, typically made of carbon or graphite, ensure electrical contact with the rotating commutator. The shaft transfers the mechanical energy to external machinery. DC motors come in 3 primary types, each with distinct characteristics. The shunt motor has field windings connected in parallel with the armature, providing constant speed under varying loads. Series motors, with field windings connected in series to the armature, offer high starting torque but variable speed. Compound motors combine series and shunt windings, delivering the advantages of both: high starting torque and relatively consistent speed across different load conditions. Let's explore the working mechanism of a DC motor. When DC voltage is applied, current flows through the armature winding. This current-carrying winding interacts with the magnetic field created by field windings or permanent magnets. According to Lorenz's law, this interaction generates a force that acts on the armature, causing it to rotate. The commutator plays a crucial role by periodically reversing the current direction in the armature windings, ensuring continuous and smooth rotation. Back EMF is a fascinating phenomenon in DC motors. As the motor's armature rotates, it induces a voltage in the armature winding that opposes the applied voltage. The back EMF is calculated using the equation E equals K multiplied by phi and N. Here, E represents the back EMF, K is a constant dependent on motor design, phi is the magnetic flux per pole, and N is the armature speed in RPM. This process helps regulate motor speed and prevents excessive current flow. Understanding motor speed and torque is crucial in DC motor operations. The motor speed is determined by the armature voltage divided by the field flux. The torque generated is proportional to the armature current, calculated by multiplying a constant K, the magnetic flux, and the armature current. These equations reveal how changes in voltage, current, and magnetic flux directly impact the motor's performance and mechanical output. DC motors find extensive applications across various industries. They are integral to electric vehicles, providing smooth and efficient motion. In industrial settings, they power conveyors and hoists for lifting and transporting goods. Household appliances like electric fans and blowers rely on DC motors. Electric lifts and escalators also benefit from their high starting torque, making them versatile and essential in modern technology. While DC generators and motors might seem similar, they serve distinct purposes. Generators convert mechanical energy to electrical energy, while motors transform electrical energy into mechanical energy. They operate on different principles. Generators use Faraday's law of induction, while motors rely on Lorentz force law. Their commutators serve different functions. For generators, it converts AC to DC, and for motors, it enables continuous rotation. Speed control is critical in DC motors for various applications like conveyor systems and electric vehicles. The motor's speed depends on 2 key factors: armature voltage and field flux. Different motor types require different speed control methods. The primary goal is to optimize performance by precisely managing the motor's rotational speed across various operational conditions. Shunt motors have field windings connected in parallel with the armature. Their speed is controlled by adjusting field flux or armature voltage. The speed equation shows that motor speed is inversely proportional to field flux and directly proportional to armature voltage. This means reducing field current increases speed, while increasing field current decreases speed. Multiple methods like flux control, rheostatic control, and voltage control can be employed. Flux control is a fundamental method for speed regulation in shunt motors. By varying the field current using a variable resistance, motor speed can be adjusted. Reducing field current decreases flux, causing the motor speed to increase. Conversely, increasing field current raises flux, subsequently reducing motor speed. While simple to implement, this method can decrease motor efficiency due to power loss in the variable resistance. Rheostatic control involves using a variable resistor, or rheostat, in series with armature or field windings. By adjusting the rheostat in the armature circuit, you can change the armature voltage, thus modifying speed. In the field circuit, it influences the field current and flux. This method is straightforward and works well for moderate speed control in smaller applications, though it does introduce some power loss. Voltage control is the most efficient method for managing shunt motor speeds. By directly adjusting the armature voltage, motor speed can be precisely controlled. Techniques like series voltage regulators and pulse width modulation enable smooth and accurate speed management. This method offers significant advantages. It's efficient, causes minimal power loss, and provides very fine speed control. However, it typically requires specialized equipment like variable power supplies or PWM controllers. Series motors have a unique characteristic where field windings are connected in series with the armature. Their speed-torque relationship differs significantly from shunt motors. The speed equation for series motors shows that speed is inversely proportional to field flux, which is directly related to armature current. As load increases, armature current rises, affecting the motor's flux and subsequently impacting its speed. For series motors, speed control primarily involves manipulating armature voltage. By reducing the armature voltage, the current through field windings decreases, which in turn reduces field flux. This reduction in flux results in increased speed, since speed is inversely proportional to field flux. This method is particularly useful in applications requiring high starting torque, such as electric trains and cranes. Field control in series motors involves inserting a resistor in series with the field winding to reduce field current. As field current decreases, the magnetic flux diminishes, leading to an increase in motor speed. While simple and cost-effective, this method has limitations. Speed regulation can be poor under varying loads, especially at low load conditions, making it less reliable for precision applications. Shunt and series motors exhibit distinct speed control characteristics. Shunt motors maintain relatively constant speed across different loads, making them ideal for precision industrial machinery. Series motors, in contrast, experience significant speed variations with load changes. Their speed increases as load decreases, making them suitable for high-torque applications like electric vehicles and cranes. We've journeyed through the fascinating world of DC generators and motors. From understanding fundamental principles to exploring advanced control techniques, we've seen how these remarkable machines convert energy and drive technological innovation. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.